Hello everybody, welcome to the next video in the series of Physics at Home. Today we're going to do a fun experiment using light and a lens. This is a double convex lens, meaning the two surfaces of this lens are like this. So physics tells us that when the light passes through this lens, then the lens is going to bend the light and then they can meet together at a focal point. So just like there is light could pass this way, it could also pass the other way. So this lens has two focal points, right? One behind the lens, one front of the lens. Okay, so we're going to use that information and try to form an image of an object. Okay. So object in this case is this plastic slide here. And what I've done is I've put markings there, and 0, 1, and 2, those are in centimeters. I've also put an arrow here, and to indicate where the arrow has been put, I put a little tape so that I would know how this is going to be placed. Now this would be my object. Using a binder clip, I'm going to place this object right here. So make sure that it's as vertical as possible, and the lens I'm going to put in front of it. Okay, there we go. So these clips here, they won't interfere with the experiment that we're trying to do. Now we need to shine light, for which we're going to use this flashlight here. Now the camera needs to be adjusted a little bit, so give me just one moment. Okay, here now you can see the image formed, and we could make sure that the image is sharp. There we go. So see what's going on here for a second. Oops. See, it's supposed to be 2, but it is upside down. Not only that, but the face, you see the tape right here. This is where the arrow was supposed to be pointing, correct? But look at the arrow right here. Now it has turned 180 degrees. So this is how this image is formed. So if you think about it in this fashion, that if this is the left here and the top here, then this gets going to get turned 180 degrees, so that now the top, whatever which is pointing top now is pointing down, and whatever is pointing left gets turned and points to the right. Now 2 was supposed to be on top, and also arrow was 2 was supposed to be down, arrow was supposed to be on the top. Now the 2 is on the top and arrow is on the bottom, so that tells us how this image is formed here, like how the rotation works. Now for this situation, we need to measure 2 items. First one is called as the object distance. Object distance is the distance of the object from the lens. Okay, so we need to know how much this distance is. Right. So it is, I'm gonna eyeball it here, and from this point to this point here, so about 12.8 centimeters. Alright, so D subscript O, 12.8 centimeter. Sometimes it is also called as S, depending on which textbook you're using. The second distance we need to measure is the image distance. Okay. The image distance here is distance of the image from the lens. Okay, so the lens is just here, so this is 30. And we need to go farther down. So this is 38.8, 38.6. That is D subscript I. 38.6 centimeter, which is also S prime. Okay. There's one more item that I'm going to measure, is the size of the image. Okay. So I know that originally this was supposed to be 1 centimeter, correct? 0 and then 1 and 2, right? So the distance between 1 and 2 is supposed to be 1 centimeter. I want to know how much is the distance now. About 3 centimeters. Okay. So this is gonna be Y prime, 3 centimeter. We know Y was supposed to be 1 centimeter. Y is the object size and Y prime is the image size. Now, using all of this information, in the next section of the video, we're gonna see how this lens is forming the image and how we are gonna use the focal length aspect of this, and then using that we can figure out what is the focal length of this lens. Okay, so this is a setup here where we see the lens and there is a parallel set of light rays falling on it. What the lens is going to do is going to bend all of these rays in such a fashion that they're going to all meet at one single point. The distance of this point from the axis here of this lens is the focal length of that lens. Now, parallel rays of light can be considered from coming from a distant star, for example, or something which is far away. So, looking at the way these rays are traveling, you can see that the top here, the ray at the top, gets bent most, and as you get closer to the center of the lens, then that ray which is passing to the center goes undeflected, okay? Just as that. The opposite of this could also be true, that you could have a light bulb sitting at this focal length, and then all of the rays of light which are gonna come out from this light bulb, they will all fall in this lens, and they will get bent in such a fashion that they will all be parallel to each other as they go out towards left. Now, when we ran the experiment, this was our data. Our object height Y was 1 centimeter, or object size. Sometimes this is also used as HI, or height of the object, depending on which textbook we use. S here is the object distance, which is the distance of the object from the lens. And image distance was 38.6, and image height, or the size of the image, was 3. Now I put a negative here, to which we'll see why in just 1 minute. Now this right here is the formula for the focal length of a lens. So 1 over object distance plus 1 over image distance equals to 1 over the focal length. So when we plug in 12.8 and 38.6 here, then we get the focal length as 9.6 centimeter. Now we want to see how this image was formed, geometrically speaking. This here is the setup, which is drawn to the scale. What I did was, you see this blue line here, the length of this line is about 12 inches. And what I did is I added the object distance, which is the distance of the object from the lens, which is this distance S, plus the image distance 38.6, which is from the lens to the image. 2 together is about 51.4 centimeter. And originally the blue line is 12 inches long, so my ratio is 51.4 centimeter is 12 inches. Using this ratio, now I am converting all of my object image and all of these distances into appropriate lengths of inches, so which I could then use to draw all of these pictures to the scale. Now let's see what's going on. Object here is this black arrow standing upright. Okay, so if object is standing upright, the length or size of that object is considered as positive. There are three rays of light that we can consider, which will start from the top of this object. First ray of light, which is going parallel or horizontal. Now we saw here that a parallel ray of light will get bent in such a fashion that it will go through the focal point. And this lens here has two focal points, one in front of the lens and one behind the lens here. So this parallel ray of light is going to get bent and going to go through this focal point. As it continues its journey. What we saw that when a ray of light passes through the center of the lens, it passes through unbent or unhinged, right? So when it starts from here, the second ray of light, it's going to go through the center of the lens, so it will not get deflected. It will pass through just as is. And as you can see, these two rays meet at this point right here. Yeah. We could also think about a third ray of light, which we don't really need it, but from theoretical perspective or geometric optics point of view, a third ray of light which starts here and then passes through the focal point before it hits the lens. Okay, so think about a situation as if a ray of light which begins here and then goes through and hits the lens. What we saw is that that ray of light becomes horizontal, right? The same here. As you can see, it hits the lens and it becomes horizontal. All these three rays of light, they're going to meet at this point here. And this is the point where the image is formed. Since this is upside down, is the reason why we use negative as the sign here for the size of that or height of that image. Okay. So given this information, now we're going to look at one more equation, which is the magnification. And the magnification, M, is how much the size of the image compares to the size of the object. Okay, so as you can see here, y prime over y, which is the image size over object size. So if M value is higher than 1, then it has magnified. And if the M value is lower than 1, then the image has shrunk. Correct? Looking at our data, we definitely saw that the image was magnified and it was inverted. Correct? So inverted here would mean that it is a real image, because these rays of light, when they pass through, they meet in the real world. Okay? That's the idea behind calling an image a real image. Now with this information, now let's look at, let's calculate the magnification M, which is negative S prime was 38.6 divided by S, which is 12.8. And this turns out to be negative 3.016. This is the magnification. It's a ratio of size over size, right? So it does not have any units because the units cancel out. So this is a dimensionless quantity. So this magnification is also y prime over y. Yeah. And we saw earlier that our object height or size of the object, the 1 centimeter in our object became 3 centimeter as an image, correct? So this one here is the value of y, correct? So if we bring it to the left, then negative 3.016 you multiplied by y gives you y prime, indicating that 3.016 multiplied by 1, which is negative 3.016. This is y prime. So using the information for s and s prime, we calculated the magnification m, which then the second formula for which we used to calculate the size of the image. The measured size of the image was negative 3. So now here we can calculate the percent error. So which is the absolute value of the difference between the two. So negative 3.016, and then negative times negative makes it positive, and divided by the expected value here. Okay, so 3.016. Again, here we could use the absolute value of the magnification here, or the size. So this now this is supposed to be multiplied. More appropriately, I could make this whole thing as a absolute value, which is probably better that way. And multiplied by 100. Which you would see it's going to be a pretty small error. So 0.016 over 3 times 100. Oops. It's about 0.53%. Yeah. So this is how this experiment works. That you have an object and you form an image, and the pieces that you see, you probably can buy those at a hardware store for less than $5, and you can run this experiment at home, and then you can try different sizes. Now, due to the video constraints, I could not show another version or another size of the image where I could have this lens here. I could have this lens here move farther away, where now I could form the image, but it would be smaller than the object here. Okay, but again, because of the video, I could not show it to you. But if you're trying it at home, then please look for that second smaller image. Okay. I hope you enjoyed this video, and next week we're gonna run a similar experiment but with mirror.